Good morning, everyone. I'd like to start this webinar. During the webinar, there are two boxes at the bottom of your screen. One is the chat box, which you can use to just general messages, any technical issues you have with sound or visuals, use there. There are people monitoring that box to see if they can help. There's also the Q&A box, which allows you to pose questions for the speakers. We will have a panel Q&A session at the end, and that will allow us to answer the questions there. Can you give me 1 second? Oh, God. Some of the joys of broadcasting from home, the dogs. So the Q&A box, pose questions in there for speakers. If you could add the speaker's name to the start of the question, it will help us align those. The webinar will be recorded, and after the webinar you will get a feedback form, and those who give us the feedback form first will be first in line to receive the recording and the event materials. So I'd like to welcome you all to this. This is the first of a series of webinars being organised by KTN and by EPoSS. You'll hear from both of those shortly. So this one is on digital industry, and the next ones are on the mobility and healthcare sectors. In parallel with the webinar on Zoom, we run Meeting Mojo, which allows you to message other delegates and arrange video conference sessions for this afternoon, video conference sessions. The link is actually on the slide now, but we'll post that link in the chat window. I know many of you have registered for Meeting Mojo. For anyone who hasn't registered, they can use that link to register now. So today's program, we've got 7 presentations in all. The first 2 about the people organising the event, KTN and EPoSS, and then a series of presentations that cover this subject area in a variety of details. And with that, I'd like to hand over to Nilam to take us through the first presentation about the KTN. Nilam.
Thanks, Nigel. I'm just going to share my screen with you. Brilliant. Okay, so yeah, my name is Nilam Banks. I'm part of the Enabling Technologies team. In August, the KTN launched its 5-year strategy and its branding. So if you're a regular to these events, you'll see that our presentations have slightly changed and gone a little bit green. I'm just going to show a short video just to show you the vision. Just give me a moment. Yeah, sorry about that. So yeah, the KTN are all about connecting for positive change. My name's Nilam and I'm part of the Enabling Technologies team, and my role is to look for cross-sector opportunities for the communities within our team, and that includes electronics, sensors, photonics. So it's all about giving you the opportunity to explore new areas. The way that we do it in the KTN is that we have deep expertise. We've got people who cover all areas, all different sectors. So if you wanted to contact me, I can introduce you to these experts within these areas, and they'll be able to potentially show you new opportunities. In this presentation, what I've done is I've looked at specific areas that we work in that will be relevant to you. So although this is only a snapshot of what we do, so if you do want to know about other areas, please contact me. So yeah, we have deep expertise. Areas that I thought that would be of interest to you. We do have an AI robotics area within our website, and they do have regular newsletters. So if you want to know about the latest opportunities, please subscribe to that. At the moment, they're doing a lot of digital business meetups that may be of interest. We also have the Manufacturing Made Smarter program. That's all around digitizing the manufacturing sector within the UK. At the moment, we've got the Smart Factory Expo, which gives businesses the opportunity to showcase their technologies to manufacturers within the UK, but also the enabling team are running an investor readiness program, which you can get involved in, which will allow you, which will help you to become pitch ready to potential investors. There's also opportunities in precision medicine that you may want to explore. We're also all about powerful connections. So predominantly we do that through events like this one. So you've got the opportunity to have the one-to-one meetings on Meeting Mojo, and also funding opportunities. These are generally through Innovate UK and some European fundings, but will help you create a consortium. In regards to the events, I'm going to do a shameless plug because I'm running the Enabling Green Recovery event. That's all around giving you an idea of the challenges local authorities face when meeting their net zero objectives. So the next one may be of interest because we're working with Nottingham City Council, who are keen to trial technologies all around measuring and monitoring to make sure that they're making informed decisions for the right projects. We also have an innovation exchange. This is all around getting large organisations showcase their challenges for you to solve. So at the moment, you may want to explore that. There's a couple from the British Antarctic Survey. We've worked with many different companies, but it may be worth subscribing to that as well to see how you can help there. We're also all about future shaping. So we deliver a large number of innovation networks. So that's all around future technologies, future I guess, ideas, innovations that could change the world. I've listed the current ones that are currently active, but we're always open to new suggestions. So if you do have an area that you'd like to create a consortium, create a community around, and to explore that and what that looks like in different sectors, please get in touch with myself or Nigel. Also, another shameless plug, we'll be delivering Women in Innovation. We've got Women in Enabling Technologies event. What we want to do is understand what the barriers are for women to engage with our events so we can change what we're doing to make sure that we're completely transparent, open to accepting people from all backgrounds. So how can you be a part of this journey? Subscribe to our events, come along, well, subscribe to our newsletters, come along to our events and just join us. If you have any questions about other sectors or other areas, please contact me directly. And that's it from me. Thank you. And
I'd now like to ask Elizabeth from VDI-VDE just to tell us a bit about EPoSS.
Good morning, everybody. Hope you can hear me and you can see my screen now.
Yes, we can see the screen.
Okay, so good morning, everybody. A warm welcome from my side. It's a pleasure for EPoSS to be co-organizer of this webinar series together with KTN. And I would first of all like to thank KTN for setting this up. I think it's a really great opportunity to bring our communities together. So EPoSS, what's EPoSS? EPoSS is the European technology platform on smart systems integration. I'm office director at EPoSS. So we are running a small office in Berlin, and we do this on behalf of, just a second, our community. So what's EPoSS? EPoSS is an industry-driven policy initiative. So we are collecting R&D and innovation needs from our members, and we are defining policy requirements, all related to smart systems integration and to integrated micro and nano systems. Our members are shown here. So we are covering basically whole value chains all across Europe with regard to the European smart systems community. We have engagements from large, medium-sized and small entities in EPoSS, as well as world-leading RTOs in the field of smart systems integration. In EPoSS, we are hosting several working groups on areas like mobility, health, energy, and as we talk about today, digital industry, as well as agri-food and natural resources. And what is quite new for us now is we have lately formed a group on AI at the edge, a task force working on a white paper currently, and also organizing and setting up these webinars together with KTN. So here are some examples of what our members are doing with regard to smart systems. So in the field of industrial, medical, automotive, environmental, of course, this is just a snapshot and a quick view on what we consider smart systems and where we are at the forefront, where our members are at the forefront of the developments, and where Europe is really playing a big role in the world. So our tasks at EPoSS are really bringing together these experts and creating a common European approach on innovative smart systems integration. And so we are setting or trying to set the research priorities all together and to feed that into roadmaps. We currently have roadmap activity going on that EPoSS is chairing. That's the ECS ASRIA, that's the Electronic Components and Systems Strategic Research Agenda for the next years, which will lay the ground for electronic components and systems developments in Europe on this for successing programs like Excel joint undertaking and Eureka clusters. And based on this, we of course try to mobilize financial resources for the community. So these are basically the main tasks we have. And as Europe is going into new programs, of course, we have a lot of work currently going on with regard to Horizon Europe. We do everything to position our members and especially SME interests in future programs. So we have published a white paper on 12 commandments for successful SME integration into European programs. We are integrating currently with Euripides for new clusters in the environment of Eureka. Which is, I think, also an interesting instrument for people in the UK with perspective of Brexit, because Eureka is an instrument where member states are funding and the Commission is not involved. So beyond that, I've shown you on the slide before already that we are active in the Excel joint undertaking, and this one is ending as well next year. So we are implementing and initiating now the successor program called Key Digital Technologies. We do this again together with two other industry associations, Eneas and Artemis. We are close to finalize the work program and the documents for this. And beyond that, EPoSS is involved in two other public-private partnerships in the 2.0 public-private partnership, successor of Equia. So this is the electric vehicles initiative, and beyond that in CCAM, which is focusing on autonomous driving. And in the field of health, we are a member of the ESTER Alliance, and of course we are looking into other application areas and initiatives and try to network further in all specific application fields our members are involved. So if you have any questions and if you want to join us, please contact either me directly or use these links given here. Have a look at the website and yeah, please get back to us for any question you might have. And once again, many thanks to KTN for organizing this webinar. Okay, I hand over to Nigel or to the next speaker.
Thank you very much, Elizabeth. And I think one of the things from the map, you might have seen that at the moment there are no UK members of EPoSS. Obviously, EPoSS does spend a lot of its time looking after European funding, but the networking opportunities by joining EPoSS and getting involved in the working groups is actually quite significant. Some of the largest companies in Europe are members of EPoSS and therefore are setting agendas that will affect all countries. So I'd now like to hand over to Mark for the presentation from ExMOS.
Hi, thanks, Nigel. Good morning, everyone, and thanks to KTN for this opportunity. I'd like to talk to you, I've got 15 minutes this morning to talk to you about some primary research we did. ExMOS is a semiconductor company that's headquartered in the southwest of the UK. Our focus is on the artificial intelligence of things, so providing solutions for the artificial intelligence of things. And we were interested to try and understand the sentiments of the engineering community, and when they were faced with the challenge of delivering on the various different aspects of the AIoT in order to really capitalize on the opportunity. So I'm going to spend a few minutes going through that with you this morning. Excuse me. So firstly, just to sort of set the scene and the reason why everybody is so very interested. I mean, we're all very familiar with how quickly our digital lives are evolving. It may be perhaps a surprise to some that since COVID has been on the scene, Actually, I think it's been an accelerator. We've seen various different digital technologies, the evolution of them accelerating somewhat faster as a result of our new normal. We've seen certainly also technology and devices becoming smarter, and we are entering a new era that doesn't just promise a connected world, but and promises intelligence that gives us the ability to make our lives simpler, safer, and more satisfying. So the AIoT is a convergence of two, what I would call meta markets. There's artificial intelligence, which has been very prominent in the news for many years now, and also the Internet of Things, which describes a ubiquitous connectivity between all sorts of products, very fragmented collection of markets with products that all connected together through the internet. So this is a huge opportunity. The convergence of these two massive markets is a huge opportunity. In fact, Gartner, these numbers are from Gartner, but one number that's not on this slide is that Gartner predict next year that 1 million devices that are augmented with artificial intelligence will be selling every hour, which is just staggering. So we wanted to, as a company, we wanted to explore what the challenges were to delivering on this promise, and so we commissioned some primary research to dig a little bit deeper into the thoughts and sentiments of the engineering community. So the research was 200 electronics engineers. As you can see, they came from various different parts of the semiconductor business with various different careabouts. And we asked them their views on the technology building blocks, barriers holding the market back, and their own design and commercial priorities. So over the next few slides, we'll talk through some of the key findings. But one of the things that's interesting to me is that when you survey engineers, you're not surveying the group of the cohort of people that are primarily interested in really pushing the boundaries of possibility, the visionaries that sort of express what the world might look like in 20 or 30 years' time. You're talking to people that are actually responsible for turning those visions, turning those concepts into reality. And engineers are a pretty discerning group. So you get a sense of where we are on the hype curve. And our research shows that the engineers are acutely aware of the potential of the AIoT. 40% is a big number in a survey like this, particularly when you consider that that's the prediction of the AIoT radically changing technology for the better. And even more so, engineers saying that the AIoT is critical for improving the way that we interact with technologies. Now, in some ways, obviously, people respond as people, as well as members of a certain cohort, and we're all very aware of the hijacking, if you will, of the previously somewhat unintelligent wireless speaker and its transformation into smart speakers. That's part of many of our everyday realities, and that's just a single demonstrator, the thin end of the wedge, if you like, of how intelligence is going to proliferate into things that we find in our everyday environments. So this set of results gives us a sense for the attach rate, or for the anticipated attach rate of AI in various sectors. It's a healthy attach rate. It's interesting. It's between 20 and 40%, but I think this actually probably shows some conservatism. And there are various industry commentators talking about this phenomenon. The most recent one I saw was Dr. Naveed Shawani, who's in fact at the time was the president and CEO of Sci5. Now he's the chairman. He showed a study that by 2025, the attach rate of intelligence to endpoint devices would be 100%. So whether it's 20%, 40, or 100%, it cannot be ignored. Over 80% of our respondents said that AI will increase their competitiveness, and the prizes on offer in the semiconductor industry are huge. The semiconductor market today is just under $500 billion. So there's a significant potential for those that can harness AI and deliver on that promise of additional competitiveness. So amongst the people that we surveyed, we're pretty confident to say that they care about this issue. And many of the engineers, I suspect, are thinking very carefully about how they deliver on this, and possibly already involved in projects in this space. So let's take a quick look through some of the devices and what they might look like in our day-to-day lives. Starting in the home. The home's perhaps the most familiar use case certainly in today's world. The primary advantages are about convenience, but also increasingly safety. A classical example is the kitchen. Voice interfaces continue to be one of the primary deployments of artificial intelligence at the edge. And voice interfaces are really good at adding, convenience where you've got, busy eyes, busy hands. In the kitchen, you might have just been cutting fresh meat, so there's a hygiene challenge. They might be covered in flour, so you don't want to touch your technology or your appliances. Or it might be you're simply multitasking. You're doing multiple things, and you want to set a timer, or you want to switch off a hob or something of that nature. Primarily about convenience. What we're seeing emerging now, though, is the safety aspect as well. To stay in the kitchen for a moment, we can do human presence detection, so we can control the availability of appliances, but we can also detect whether or not the human that is present is a child or an adult. And if there aren't any adults in the room but children are present, we may choose to disable the oven, for example, or disable the hob, or disable the ability to close the door on the washing machine, for example. So those sorts of use cases are becoming very, very accessible. And increasingly, we're also seeing technologies that allow the elderly community to age in place. So looking after people that might be living alone, that perhaps have mobility issues, drug regimes, things that are complex to manage, that can be managed using this type of artificial intelligence deployed in the home. So lots and lots of use cases. It's not just about wireless speakers, and certainly in the future, you're going to see a lot more diversification there. In smart buildings, the use cases have historically revolved around efficiency and security, now increasingly safety again. We can use presence detection here, facial recognition, voice biometrics to enhance security, but we can also optimize the energy footprint of our buildings and the utilization efficiency of meeting rooms, for example, by understanding where people are and how many people are there. Of course, in today's world, we're also now concerned about how we interact with that environment, and specifically whether or not we use touchscreens and the like. There's an increasing emphasis on contactless interfaces. So once again, voice has its part, a very strong position in the smart building. Smart cities share many of the attributes of smart buildings. Significant efficiencies can be gained through the understanding of the flow of people and traffic, not just efficiencies in time, but also even the benefits of directing traffic to, for example, parking spaces that are available on demand, so that we save a tremendous amount on fuel combustion whilst people drive around currently looking for parking spaces. So there's very, very strong value propositions in the smart city, as well as the ability to manage individual security, either passively through monitoring environments or actively through providing some interactive support. And this is, I guess, a somewhat more trivial example of somebody not knowing how to find something, but there are obviously more critical areas where support can be managed and security can be managed more interactively using artificial intelligence at the endpoint. Again, contactless interfaces, this is another shared environment, so contactless interfaces will play a major role here as we become increasingly concerned about hygiene risks in shared spaces. And this is the last example. There could be many more, but I think this is a great example, and I think the subject of a number of talks later on is the smart factory industry 4.0. Efficiency and safety benefits are obvious in a factory context, and we can use predictive maintenance, looking at various artifacts of machines in operation to determine whether or not they need to be maintained. We can use defect detection on the production line for higher throughput and quality. Human identification and presence detection, again, looking after people's security and safety in the presence of industrial plant on the factory floor. And of course, natural language interfaces can increase ease of use in this context as well. So we could go on. I've not got a slide on automotive, which is another one of those areas where there's obvious benefits. The point here is the application space is huge and fragmented. So lots of opportunities, but many challenges and some barriers to real explosive growth in this sector. Now, this is a comment, this set of responses relate to artificial intelligence and endpoint devices, but not so much necessarily to where that intelligence is delivered. And I think a lot of these responses reflect perhaps a bigger issue with the intelligence residing in the cloud. Of course, data security is always a problem, always a concern. We're gathering enormous amounts of data with increasingly complex and capable sensors. And we care about how that data can be used. Of course, that's quite natural, and that's on a personal level, but obviously also on a commercial level. So the community that we surveyed, they care about bandwidth, so slightly closer to home, perhaps thinking about the technical challenges with all of those sensors producing an enormous amount of data. You know, how does our network scale to transfer that data to the compute resource? How long does it take if we're controlling the interactions of humans with machines, and more critically controlling the behavior of machines that might move? Then latency is extremely important. We want to be able to guarantee a response in an appropriate amount of time. For a human being, it might be a quarter of a second. For a machine, it might be milliseconds, or possibly even microseconds. And then there's scalability. You know, scalability touches a little bit on the bandwidth point, but also the scalability of compute. A lot of this technology requires enormous amounts of compute, and can we deliver it? Can we deliver it using the existing sort of centralized model? So moving intelligence to the edge solves for many of these challenges, but actually raises some new concerns at the device level. So people that develop devices and develop semiconductors for endpoint devices, they have some familiar challenges. Power consumption is always one of the big ones, trying to reduce power consumption so that we can be battery powered, so that we can deploy these devices into the field under battery power for significant periods of time. We're always worried about design complexity, and the flip side of that coin is how long is it going to take us to get this product to market, because these markets tend to be very volatile. You need agile solutions and techniques to get those devices to market, to hit those demand curves. Always we're worried about bill of materials. I mean, never more so than in consumer, but there is all of these markets are concerned significantly with the cost. And then as we move intelligence to the edge, we're placing unprecedented demands on processing power at the edge devices. So all of these things relate to each other somewhat. Obviously, processing power, increases in processing power typically come hand in hand with increases in power consumption, design complexity, and BOM costs. So they're all related to one another. So the question is, whilst making these devices more intelligent has the potential to improve the competitive advantage of products and change the world as we know it, how do we solve for these very difficult challenges? How do we make sure that we can continue this march towards delivering these genuine benefits across our society? So one of the things that was clear amongst our respondents was we need to reduce our reliance on the cloud. I think 70% of them agreed that more on-device intelligence is needed. So that really validates amongst the engineering community that there is a huge market for intelligence at the edge. It is one that's very fragmented. It requires massive increases in processing power, but not at the expense of power consumption or cost. So it's a bit of a challenge, and this is where this is really, you know, on our front yard as a semiconductor company. And our conclusion when faced with those challenges was that we needed a new kind of processor. And this is my opportunity for a shameless plug. X-Core AI is a third generation of our X-Core processors. It's a design, a technology that we own, that was designed by the University of Bristol. We originally designed X-Core to tackle the challenges of the Internet of Things. So the Internet of Things is a very fragmented space where you've got lots and lots of different applications communicating with each other through the internet. So we built a very high performance controller that had the ability to execute all of the control features, and uniquely also to address many of the challenges of connecting to different sensors and different actuators and so on in that space. In the second generation, we added signal processing to improve our capability of processing sensors, processing audio data streams and other data streams from different sensors. And finally, in our third generation in X-Core AI, increase the level of performance in every one of those areas, but also added artificial intelligence capabilities. So now we have XCore AI, which is the only device that allows engineers to define their whole AIoT system in software, which tackles both the performance demands, but also the compulsion to get to market quickly and adapt in a rapidly evolving space. So we solve for all of the challenges that we've looked at. The level of the 4 classes of compute on XCore AI allow us to integrate many of the discrete components that you would normally find and optimize the BOM. Since the inception of XCore, we've always had the lowest latency of any microcontroller or microprocessor on the planet. We deliver low energy. We have a root of security that delivers privacy and so on. But critically, what we did with our latest generation of products is really push the accelerator pedal on performance. So we're delivering 32 times the AI performance, for example, of a Cortex M7 processor running at 600 megahertz, which is the sort of contemporary comparison point. So XCore AI is a real beast. It's designed addressing the concerns of that were echoed very strongly in that survey, for a device that's very economically available to those engineers to help them to solve the challenges that they're facing. So this is my last slide. Hopefully, we're all observant of the impact that artificial intelligence is having in our environment already. But I think we're reaching a tipping point. I think COVID is a catalyst for that. And we'll see that not just in convenience, but also safety and security, we'll see real impact in the future from deployment of intelligence at the edge of the network. It depends on numerous players in the ecosystem stepping up and delivering solutions that are cost effective and secure, that don't rely necessarily on cloud connectivity. They may be augmented by cloud connectivity, but they don't rely upon it. And I'd invite you to come and see us at xmos.ai to learn more about XCore AI, which is a truly distinctive product that is absolutely targeted and tuned and tailored for this space. So that's me. If you want to know more about the Edge of Tomorrow report, it is available on our website, and there's more detail there, as well as all of the statistics and questions that were put to our audience. Finally, thank you very much for the opportunity to talk.
Thank you very much, Mark, and that gives us a good introduction to today's topics. I'd now like to hand over to Nicholas from NXP. I'm not sure about having 2 semiconductor manufacturers back to back, but I'm sure they'll play friendly. Nicholas.
All right, I hope my camera works at least for a minute. I know it will cut out in just a second because my browser doesn't like me. All right, but I'll return later on. So let's see. So just to briefly introduce myself, so I'm working with NXP as the... Can you actually see it?
No, yes, we can now. That's it.
I hope so.
Showing now.
All right, beautiful. Sorry that the camera is gone. As I said, the browser doesn't like me at all. So just as a bit of background, so NXP is a pretty large semiconductor company. So we've got 30,000 employees worldwide, but the headquarters are still in the Netherlands. Myself, I'm sitting in Munich. Lots of my colleagues are over in Hamburg as well, of course. And yeah, we basically provide processing power, connectivity options, security, and so on and so forth for a range of different sectors. We are pretty big in automotive, but there's also a growing and significant presence in industrial automation, mobile, smart home, and so on and so forth. So we are in this very interesting position that we try to look at the technology across different fields. And personally, I come from a background in collaborative robotics. So before I joined NXP, I was working on safety systems. So that makes it quite interesting to see how now AI is sort of moving throughout the whole field and changing things. And we can already see quite a few applications in industrial automation where machine learning is sort of emerging from the data centers and making its way closer to the application, closer to the assembly lines, the conveyor belts. So you'll often sometimes see vision systems which are already trying to pick up anomalies happening on the factory floor, things like package detection, QR code detection. I think that's pretty commonplace by now that you don't send up the data to the data center, but do that on the edge. We see increasingly people using visual defect recognition on assembly lines. Of course, there's also big things like voice and sound anomaly detection. So yeah, you have alarm analytics. For example, you try to figure out, is that breaking glass? I've got no idea why somebody would put baby crying on this slide. I hope you never have that in your factories. And of course, I mentioned anomaly detection. So that's the growing field where you do things like, especially in agriculture, where you try to identify pests out on the field, do quality control and analytics on the shop floor, motor performance, motor health supervision. Those are rising topics. And I think it's interesting to see how this sort of ties in with the waves of innovation in AI. So a lot of you are probably familiar with that, but let me just briefly recap. So in the late 40s, early 50s, we saw this first wave of AI rising, where we basically had a lot of the concepts we still use today established in academia. And then sort of interest dried up for a while. Then we saw the rise of the expert systems. So systems running in huge data centers and especially trying to filter database scale information. For a while, they couldn't deliver on the promise, so funding froze up again. And now we are sort of in the third wave, where we see deep learning, convolutional neural networks, massive data architectures. So recently, a couple of people have been sort of wondering, well, are we headed for another sort of downturn in this field? And there are some people asking, okay, where are my self-driving cars? Why are we still not flying on Mars? That sort of thing. So yeah, those are definitely justified concerns. There is a bit of a stall, I'd say, in the momentum of new algorithms coming up. However, if we look at the other side of the game, if we look at the actual compute devices on the field, we can see that these concerns are probably not that well funded. So just to sort of iterate over the last wave. So the first wave, that was basically a time where we did not have much compute at all. So a lot of that work was academic. It was more on paper than out in reality. Then the second wave, okay, we started seeing the compute moving from the data center, at least onto the desktop. So we started to see the rise of the PC, the personal computer. And then the third wave, well, there's an interesting thing happening there, because suddenly compute was in everybody's pocket. We had cell phones which were connecting to huge data centers where you could crunch all that data. And what's happening now is that we start seeing the compute being divided far more widely, that we basically escape from the cell phone and at any waking hour are surrounded by devices which offer computation capacity. And I think this is really something which is going to drive the next wave. So there will be sort of like gradual migration over into a fourth wave, where we will maybe change the algorithms. But I think the biggest change is actually that we are moving away from the data center out into the fabric which surrounds us in everyday life. So this is really going to stretch across all the verticals, from the consumer over the smart home, over mobility, of course, where we're looking at driving assistance systems, into larger scale connected systems like smart cities, smart industry, and so on and so forth. So today, of course, we are interested in smart industry. This is digital industry panel, so I'm going to focus my story a little bit on that. But I think it's sort of helpful to remind ourselves that AI grew in the clouds. So a lot of what we see today, a lot of the algorithms and a lot of the use cases, they are originally media-centered, where people upload large amounts of photos, for example, from their smartphones. They require data centers to do the processing. And that really gave rise to this ecosystem we see today with a bunch of big cloud operators, where we have tools which are mostly focused for designing algorithms and systems running on these large-scale data centers. We also saw a tendency towards heavy and powerful model architecture. So, for example, transformer models, those can grow pretty big. Now, as we sort of get out of the data center, as we move down below the clouds, where do we find ourselves? Well, it's a bit of a wilderness, and there are different rules at play here. And I want to sort of take a look at them over the next minutes. So we're going to see a lot more unreliable connections, for example. Everybody who's driven a car in the Bavarian countryside knows that you cannot rely on connectivity. So you need to bring your compute with you. You will face power constraints, especially when you're running on battery power or under thermal constraints. You will need to deal with far more unstructured and unpredictable environments. That's a lesson the guys in automotive learned early on. You'll need to make very real-time and robust decisions. So you really have one shot to get it right, and you need to get it right before something significant happens. And of course, you need to deal with far more hostile actors. So that could be people trying to spoof your system, but that could also be people just attaching a debug probe to your new system, to your new product, and just trying to download whatever intelligence you put on there and put that into their own system. So all of these are things you should take care of and think about early on. So another thing to think about, which edge are we actually looking at? So the cloud, I think everybody's pretty clear on. That's sort of like a pristine data center sitting somewhere in a protected space. Then one level below that, we have the network edge. So that's something which may or may not connect to the cloud, to the larger world. And it's what we, for example, commonly see in robotic systems, what we also see in car systems. And then, of course, there is the application edge, which, for example, if you're sitting at home, that could be your smart speaker. When you're sitting in a car, that could be the camera monitoring the road in front of you. So there we have different scales at which we operate. And now the question, of course, is why are we going out of the data center in first place? So Mark already sort of summarized a few of these. So we have the high round trip latency. So every time you want to talk to the data center, that takes time. And if you have a round trip of, let's say, 500 milliseconds, and you're driving in a car which is going 100 kilometers per hour, within those 500 milliseconds, you'll have traveled quite a stretch. So if you have something critical, you want to do it quickly, and that may require you to go on the edge. You oftentimes will find limited bandwidth, especially if you have lots of sensors connected. So if you have, let's say, 500 smart cameras in your factory, you don't want to pipe that all up to some remote cloud center. You may have, of course, limited connectivity, especially in mobile applications. So it's not only cars, but also think about AGVs, so automated guided vehicles. Think about drones, which may be flying over some fields. And of course, once you have a data center, you have associated cost, and there's also the issue of privacy. So whatever you upload can be intercepted on the way. So it makes sense to keep stuff which you want to keep private on the edge to start with. So where do we now place intelligence? So in a typical AI system, you'll find different stages. You'll oftentimes find some sort of pre-processing of raw data. Then you compute some sort of descriptor out of that, for example, using a convolutional neural network architecture. And attached, you'll find some sort of classifier or regression or, well, what have you. So we can, of course, basically take all of these steps and put them right on the application edge. That's what people oftentimes do with smart cameras, where you try to detect whether there's a defect in your product. That, of course, means that you need to package everything into this one device. But oftentimes, it's smarter to actually distribute things a bit further. So let's say you have a huge printing press, which you want to instrument. You start attaching, let's say, 50 vibration sensors to that press. So now you can start thinking, how do you actually distribute the intelligence? So for example, you could do a very first pre-processing right at the vibration sensor, then send up that data over the maybe slightly constrained bandwidth up to the network gateway. There you basically take the data coming from all the sensors, compute a descriptor, which is also time synchronized, which is another tricky thing to get right. And then you just basically send up that descriptor to the data center. And the data center maybe monitors not just one printing press, but 50 of them, or 100 or 200. And then you can basically take that reduced data and work classification, regression algorithms on that to get further insights. So really going to the edge, it's not a binary decision. It can be very gradual, but you of course need to make sure that your architecture and management complexity stays within manageable bounds. So just to sort of iterate, when you're running on the edge, we like to think in these sense, think, act cycles. So on the sensing side, you need to deal with far more noisy data, with weakly structured environments, which are also not very fully observable. Then when you run the inference, when you apply the intelligence you have, You have to consider that you stay within your power budget, that you fulfill the real-time limits, that you do not go over the bandwidth you have available to communicate. And of course, once you decide to act, you need to consider that there's a single-shot success. If you fly the drone into the wall, the drone is gone. And you are obviously bound by the physics, and your action will change the world. So if you pick up a box, you need to recompute your maps of the environment, because the box which currently occupies the space is gone. So that really sort of has an impact on how you act. And well, sort of you need to make sure that you also think about security and safety much earlier than you would do in a typical data center application. So lots of different inputs into the design process you need to consider. I mentioned the local decision making, which really comes from real-time constraints you may have or connectivity gaps, the unstructured environments you will encounter, security and safety. That's really crucial to get right, especially when you have an embedded system. You need to consider that whatever expensive model you trained, you put that on a chip and you put it out in the field. So if there's anything you can do really easily to increase your security, just start encrypting your model when it's not being used. Don't put your intellectual property out unencrypted. So that's like a very first hint you to take. Also, something people often overlook, developer expertise. So you may have a great idea, you may have a great architecture, but do you actually find the right people on the job market right now? So that's also something to keep in mind. So enablement is very important. People tend to overlook dataset availability, especially in industrial applications. So when you are running a photo recognition engine on the net, you can sort of expect people to upload plenty of pictures with cats and dogs on them so that you can train. If you're running an assembly line, which turns out 100 pieces an hour, you just don't get that scale of data sets. So you need to make sure that whatever you plan, it can deal with the data set you have available. And of course, things like power constraints and overall system costs also figure into the whole design process. And yeah, then it's really the art of the system architect to find a good design balance between all these trade-offs. So some challenges to highlight. I'm just going to quickly, I already touched on some of them. So scene variability, dataset availability, that sort of goes overall into data model design. So you should have somebody who cares about that. Hardware design, that could be bill of material, power budget, the overall robustness of whatever you build. And that overlaps with safety. Safety is really, safety in AI overall, it's a much discussed but not fully solved field yet. So make sure that whatever you build, you stay within the grounds of the permitted, not within the bounds of what's possible. Because if you go to the notified bodies, let's say TÜV, and you cannot show them how your system is deterministic, you're going to have an issue with them. And of course, well, if you look at security, things like lifecycle management, overall IP protection, those are things you should definitely care about early on. So now if we sort of look a bit deeper into actually executing a machine learning model, we see that there is a sort of wide spectrum of applications and their needs. So on the low end, you have things like face recognition, which may be running in a doorbell, or maybe a bit more industrial face recognition running on a terminal of a machine, which basically only becomes active once somebody approaches. Simple speech recognition, that's pretty low end. You can do that on a microcontroller by now. On the high end, you have things like dealing with accents. So let's say you have somebody operating machinery with a heavy accent, and you, yeah, you need far more compute to deal with that. Real-time motion analysis of human bodies, that's a tricky subject. So you'll find that you may have very different needs for your application. There's really not one size fits all processor for AI, although in certain fields, especially autonomous driving, you start seeing certain packages which work well. But once you go to more differentiated applications, yeah, there's so many different things you can do. It's important to sort of have a continuum of processing options. So for us as a provider of chips, of compute engines, it's really sort of, we try to cover everything. That we basically have some low-end stuff, which is in this case Cortex-M based. Then there is this crossover section where we have, it's still a microcontroller, but it's got far more speed and it's got far more connectivity options than you would normally see, far more peripherals. And then on the high end, we go into the realm where we have these i.MX processors, multi-core. We just had one new product, which is basically packing machine learning accelerator within the chip. So that basically gets you to 2.5 teraops, which is sufficient for basically dealing with accents and dealing with complex gestures, that sort of thing. Now, the tricky part here is to sort of get the enablement right. And that's also something people tend to overlook. So we come from the data center world and everybody's using the same tool chain. And when you need something, you basically just spin up another instance or spin up another Docker container. And you usually already have these very nicely laid out pipelines. I really have to give props to the cloud operators for getting that solved in a very nice way. Once you go for embedded systems, of course, the story is slightly different. So enablement is really important. And yeah, so we basically decided to go for different degrees of enablement. I know other companies are looking, some of them are looking at more integrated approaches, some of them are looking at more hands-off approaches. For us, we sort of try to strike the middle ground where we say, okay, if you know what you're doing, we have basic enablement where you can basically do your own design, start bringing your own models and integrate that onto processors. Then we basically work with third parties, which can help you if you don't have that sort of expertise in-house. Of course, for a couple of simple things like voice recognition, Alexa integration, not that I expect to see that in a factory though, face recognition, we have sort of ready-to-play solutions where you basically just you get the blueprints, you get the bill of materials, and you can just go and integrate that into your system. And well, of course, then there's always automotive, which is living in a slightly different world since they sort of have different standards they need to comply to. So we needed to basically roll them their own enablement kit, which is now sort of integrating with the other EIQ tools. But it's really interesting to see how different levels of expertise need different levels of enablement. And yeah, covering all of that is a big challenge. All right, but to sort of get back to why we actually are moving to the edge. So just to sort of iterate quickly on the main point. So we really are going out of the data center because we want to have fast and dependable intelligence right on the edge. And we want to be independent from bandwidth constraints. So from intermittent connectivity. And of course, data privacy is a big driver. Now, I think a good webinar does not give you too many answers, but also lots of questions. And these are some questions you should start asking yourself when you think about moving towards the edge. So where do you really want to place what level of intelligence? Does it all need to be in the data center? Can you move some of it maybe into smart camera? If you distribute intelligence, how do you connect these elements? So how do you ensure that enough bandwidth is available? How do you make sure that security is certified? Yeah, and that's basically really the underlying part. So if there's nothing else you remember from this presentation, please take this away. Safety and security is not something you can attach later on. It needs to be something you think about from day one. And if you do that, you'll save yourself a lot of headache. And that goes not only for the edge, but also, of course, for the cloud, for the data center. All right, I hope I'm not too far over time, but yeah.
It would be wrong for me to comment, but thank you, Nicholas. I'd now like to move across to Adrian from Ichelin to continue some of these themes. Adrian, your slides are fine. And you're on mute, by the way. Adrian, you're on mute at the moment.
No.
There you are, heard you.
Okay. So hi everyone and welcome to this session of the webinar. My name is Adrián Morán and I work as a researcher in IoT and digital platforms at Ichelin. Ikerlan is a technological center focused on developing the technology that companies need to transform their products and services. We are more than 350 people working in sectors like capital goods, energy, and transport. We will start this session of the webinar with a minimal introduction, followed by a section describing how artificial intelligence has been evolved and moved from cloud to the edge. Then we will present some interesting use cases of running AI at the edge and finish with a sort of conclusion. Some years ago, we have been talking about industrial digitalization and digital platforms, which basically was based on connecting lower level devices like sensors with the cloud in order to get massive information about industrial processes. However, the Industry 4.0 concept goes further, looking to analyze the data, extracting knowledge and relevant information for decision making, where the artificial intelligence plays a fundamental role. Artificial intelligence has allowed us to go from talking about digital platforms to intelligent digital platforms. As an introductory point, we will start from the classical cloud edge architecture, typically comprised of a set of sensors and actuators in the lower level, an edge device or a set of edge devices in the intermediate level, and the cloud in the upper level. The intelligence in these scenarios was usually limited to control some kind of thresholds and take actions based on them. In our first AI scenario, all the artificial intelligence tasks are run at the cloud. Once the data is in the cloud, the next natural step was to process it to generate the rich information. In a real scenario, data could be in so many different forms, so this data usually need to pass through a pre-processing step in order to be ready to be used as an input for the model training. This data is then split into training and validation data for model training, and the output of this training process is a model characterized by its accuracy and loss. Once the model has been trained, the next step is to use it alongside the data provided by the sensors to generate predictions. The predictions are usually used to take decisions about whether to take an action or not. The main advantage of running training and inference at the cloud is that we have all the computational power of the cloud to quickly train our model and to perform fast inferences. The biggest issue are the need of connection between the edge and the cloud to exchange data and actions, the latency derived from such communications, and the need to guarantee the security of the exchanged data. This second approach bets for putting an already trained model through a process of optimization to take it suitable to be used in a device with constrained resources. This optimization model usually requires less disk space to be stored and less computational power to run inferences over it. However, these benefits come at the cost of reducing the model accuracy, producing lower quality predictions. Among the techniques used to optimize the common AI model, the most used one is the quantization. This technique consists in converting the standard Flow32 weight matrix to lower precision types. While keeping the accuracy of the model very close to the original one, the size of the model is drastically reduced, as well as the time and resource needed to run the inference over it. The second optimization technique is the weight pruning of sparsity, which consists in removing low-weighted connection between layers, setting the weights of such connections to 0 in the matrix. And the last optimization technique we are going to cover is the weight clustering, which consists in reducing the number of unique weights in the matrix. A number of centroids is obtained from the original matrix, and new matrix is generated with just the indexes to those centroids. Which technique or combination of techniques to use will mainly depend on the limitations set by our resource-constrained device and by our use case. In other words, how much disk space and computational power we have available at the edge, and how much loss of precision we can afford. The main advantage of running the inference at the edge is that there is no need for connection between the edge and the cloud. Another advantage is that although the inference time can be higher due to resource limitation at the edge, the reduction of communication latency usually improves the overall timing. The main disadvantage is the loss of precision in predictions and the need for a minimal computational power at the edge. The concept of distributed training or distributed computing is usually applied to those scenarios in which we have multiple devices with machine learning capabilities and we want to leverage all this computational power to train a common model. Although this concept was born to leverage computational power on servers with powerful GPUs, it can also be applied to edge devices with modest GPUs. The main objective of distributed computing is just to train models faster. The problem that federated learning has come to solve lies in where the data is and the restriction of such data. Until now, all the covered scenarios in this webinar has a centralized dataset formed from data from different sources. Federated learning emerged as a solution for scenarios in which the local dataset managed by each device cannot leave such devices for privacy restrictions or because collecting all the data at a centralized location might not be a viable option. Moreover, the local dataset handled by each device do not usually contain an enough number of samples, not allowing to locally train an effective model. The model trained locally by each device would be too attached to the local dataset, not being able to make accurate predictions on input data that is not exactly the same as the one with which the model was trained. The solution federated learning offers is to train a common model in a distributed fashion with an also distributed dataset. Note that one of the key differences between distributed learning and federated learning is that the former focuses on operations and where those operations might run, while this later focuses on data and where such data might be transformed. It is easiest to understand the federated learning concept with an example. Just suppose two factories from different companies, one in UK and the other one in USA. Both companies want to control their machines by voice and daily operations performed by is sensitive data that should not leave the installation. So each company decides to collect their own dataset and train its own model locally. The prediction of the models are really good indeed. Due to some hiring process, for example, at both companies, some UK operators are now working on the USA factory and some USA operators are now working in the UK factory. Similar factories, same machines, same operation commands, but different accents. The predictions each model does for foreign people are quite poor. This is due to each model was trained with only local data, so it's too attached to that dataset. Federated learning allows machines from both factories to share the knowledge of their own model without exchanging private data. This is achieved with a master-slave model in which factories will act as a slave, for example, and the cloud will act as master. The cloud initializes the common model randomly or from a common dataset, if any, and sends such model to both slaves. Each slave retrains the received model with their own dataset and sends back to the master only the gradient of the retraining process, which basically is how its own dataset has updated the model. The master merges both gradients and updates the common model. This process can be repeated until desired accuracy is obtained in the common model. With this common model, the previous scenario gets good results for both USA operators and UK operators. Of course, it's still possible to locally fine-tune the global model to get better results on each scenario. Some of the main advantages of using federated learning are listed here. As we have seen, federated learning is a technique that learns a shared model by aggregating locally computed updates. leaving the training data distributed and so private. The shared model has been trained using richer data than the locally stored one, and the privacy and security risks are reduced by limiting the attack surface to only the device rather than the device and the cloud. On large data sets, the communication needed to train a network are also reduced. Finally, although the proposed example focused on applying federated learning concept on edge devices, is a concept that can be directly ported to the cloud. Of course, this technique also has some weaknesses that need to be overcome. One of the main issues of distributed dataset is that the data is usually not independent and identically distributed. In our example, all UK data was in one local dataset and all USA's in the other one, which means that each time the model is retrained with the local dataset, it will move too much in UK or USA direction respectively, making model convergence slower. On the other hand, the algorithm used for merging the gradients from all slaves has a great impact in overall performance and therefore should be taken into account for research actions. Very important research line is the data privacy and how to guarantee that original information cannot be obtained from the shared gradients. Another researching point is how global and local epochs affect to our specific use case. Now we have described different ways of playing with artificial intelligence at the edge. We are going to briefly describe some real-world use cases in which we used AI at the edge. The first example is the use of AI for predictive maintenance in elevation environments. The global model has been trained in the cloud with the data collected from more than 10,000 installations and optimized to be executed at the edge. Once the model is deployed on the elevator, the operational data needed as input for the model does not need to leave the installation. Modern installation, indeed, with a minimal computing capabilities, can also fine-tune the global model with their own data to align the model to their own environment conditions. Another use case is to employ AI to detect obstacles in a train path. In this case, the model was also trained in the cloud and optimized to run at the edge, losing from 3 to 5% of accuracy. Running this optimized model directly in the train also limit the video frame processing ratio. However, the response time was drastically reduced, reducing this way the distance needed to stop the train. The main advantage of running the optimized model at the edge is that we can afford the loss of precision derived from optimization process and the latency reduction increase the safety of the whole system. It is better, in other words, it is better to detect a person with a 90% of confidence and stop the train 7 meters before than getting a 95% of confidence but run over the pedestrian. Another big benefit of this use case is that the train does not need connection with the cloud to perform the AI analysis of its video frame, keeping the system fully functional even in connection cuts, very common in railway. In this use case, maintenance technicians are provided with a mobile application that allows them to quickly identify a circuit board and access to its manual and repair instructions. The model has also been trained at the cloud with a quite complex network to differentiate between boards that might be quite similar and optimized to be executed at the smartphones. And the last use case we are going to cover is an scenario in which federated learning is used to predict failures in railway environments. The use here is that failures to be characterized are sporadic, and so the data set of each train is too poor to generate an efficient local model that predicts such failures. To overcome this limitation, federated learning techniques are used to compute a common model with the data from trains of different railways operators. As we saw on federated learning introduction, operational data of each railway operator is not shared, sharing only the local knowledge of each model, of each train. The resulting model offers a higher quality predictions that are leveraged by the whole fleet of each operator. Now we're going to summarize the main concept that we have seen related to the edge artificial intelligence. The main benefit of running AI at the cloud, as we have seen, is the computational power we have, much higher than the usually found in edge devices. As long as the model is trained in the cloud, the training data will need to leave the edge to be centralized in the cloud, typically. Federated learning is the only technique shown in this webinar that allows keeping data distributed. Regarding the cloud cost, they are reduced executing the inference at the edge and can be brought to zero with federated learning size. Theoretically, no cloud is needed with federated learning. However, one of the most common federated learning deployments is the one in which the cloud is used as master, controlling the global learning process. One of the biggest drawbacks of the cloud AI is the need for communication between edge devices and cloud to perform the inference, making it not suitable for use cases in which connection cuts are usual. And the last big disadvantage of running inference at the cloud is the latency. As we have seen, the latency is drastically reduced when running the inference at the edge. However, this problem is expected to be reduced when the massive implementation of 5G networks arrives. Also, the title of this slide is Cloud AI versus Edge AI, and the whole presentation seems to show all the benefits from running artificial intelligence at the edge. We cannot forget the cloud. Where to run our machine learning task will entirely depend on the use case. The future works towards hybrid scenarios in which some of the artificial intelligence tasks will run at the edge and the more demanding ones will be kept at the cloud. This is the spirit we followed with Ickerline Connect, where we cover all the vertical from the sensor to the data processing at the cloud with all the intermediate domains. So this is all from my side. Thank you all for your attention, and do not hesitate in writing me an email for asking any further explanation.
Thank you very much, Adrian. And that's been very useful. Those last two presentations provide much background. For those of you who remember what the agenda said, we have worked through our short break and we are running behind time, I'm afraid, but the presentations have been great. I do want to preserve at least 10 minutes for questions at the end. So what I'm going to do is go straight across to Gash and ask him to share his screen and do his presentation.
Hey, wonderful. Thank you, Nigel. Hopefully you can all hear me nice and clearly. Yes. Okay, great. So welcome to sunny Wales. I thought I have a bit of a different approach to the whole sort of topic. What you'll see here is the Waterton Technology Centre where DMIW is based. And of course, you can see some of the work that we're doing with Vactory, which is one of our products, and I'll sort of talk more about the sort of systems. And embedded systems, of course, is very important, but it's actually sort of understanding the manufacturing landscape that's even more important. So some of the things that we've done as well is, you know, we talked about things like haptic feedback. So when we're controlling robots, what we can do is basically put on our IoT devices, I guess, and we can actually be maneuvering and moving systems around. One of the new things that we're working on is starting to look at then the computer vision systems, and we're sort of starting to identify how we can actually bring some of these vision systems into the robot areas. But what I want to do, because Nigel has only given me 20 minutes instead of 2 hours, I'm going to literally sort of jump into the presentation. So if I can share my screen, screen one, and share, minimize everybody, and go into presentation mode. Okay, so hopefully you can all sort of see that clearly.
Yes.
Okay, yep. Great. So what I'm going to do is give you a quick sort of presentation from one of the events that we've run previously, which is the SME cluster events. Lots of this information is all on the websites, and of course the presentations are going to be available. So I'm really going to sort of run through a lot of these things. In terms of DMIW, what we've got is then a vision statement. Like I said, I'm not going to run through the whole thing. Rachel Davis is the person who's really driving this initiative. So again, afterwards, feel free to contact her. But the idea is to really sort of strengthen the support across the sort of business in Wales and start to look at the commercialization of innovation technologies. So DMIW is a non-profit organization. And like I said, we're working with large organizations as well as SMEs to bring research to business. Quick background again from my side. The reason we can do what we do is over the last sort of maybe 20 years, I've been in research projects. And currently you can sort of see I've run out of space to continue working on my little map. So I'll have to redraw this one of these days. Some of the key projects that we're working on at the moment is eFactory, the DIH for CPS, which is all about digital and cyber systems. And FactLog is actually sort of bringing us new technologies on digital twins and cognitive learning. So what I really want to sort of just give a bit of a background, because this is my perceived concerns as well. You know, we talk about AI, but it's always tricky to sort of put it into context. We talk about artificial intelligence when we talk about it in terms of embedded systems, shop floor implementation, office and home applications. Everybody's got this different adoption method. And even more importantly, nowadays, we're sort of starting to talk about psychology, philosophy. We're bringing that into the world of science and technology, and we're starting to blur the boundaries of ethics, bias, and reality. So it's a massive topic. And really what we're trying to do is capture human interaction. And part of that human interaction is trying to get genuine human emotional responses. I say emotional on purpose, because at the end of the day, what you see, and there's been some really great presentations, is ultimately we're still using logic chipsets to give us human capabilities. And more importantly, from my side of it, it's looking at it from the shop floor side. And what we're finding now is that, yes, we used to talk about hardware, used to talk about firmware, middleware, but now we're starting to inject code straight into programming systems, into firmware. So we're actually sort of into a whole new area. And one of the challenges is going to be to look at things like audit trails, especially when things go wrong. So it's going to be an interesting challenge. And talking about challenges, one of the things that we sort of try to do is to understand the implications of AI on things like manufacturing and processing systems compared to some of the things that you sort of typically hear about in terms of flying planes and so forth. So when you sort of look at it from the sort of human aspect, humans controlling and AI controlling, and then you sort of almost put it in the sense of endangering life, because ultimately that's a big measure. Obviously, human error will kill lots of people, as well as algorithmic errors. So the two things from the sort of the extreme of endangering life can potentially both cause problems. But when we start to look more at the process side of things, yes, people may get hurt generally with human errors, but when we look at processes, then maybe machines will get damaged. So it's not such a critical impact. And then overall, looking at data systems themselves, I mean, really when we talk about the Microsofts, the Apples, the Tatas and so on, their whole infrastructure is all based on data, as we well know. And as we sort of look at these, the transformation of data now into the cloud, you know, we're still dealing with things like legacy chipsets. We've still got old servers and so on. So cybercrime is rife because, you know, there's this transition from the old to the new. And of course, the ultimate aim, you know, somebody wants to control all of the data across the whole world. And, you know, the challenges are, how do we upgrade all of these systems? And how do we sort of rely then on AI to do the system testing? Because there's no way that humans are going to be able to deal with that side of the business. So let's step back a little bit and let's look at AI in manufacturing, because that's really where we're addressing these things. And one of the challenges is really to think about all the different ecosystems that take you from things like embedded systems, which is obviously what this group is really concerned about, and how those embedded systems then go into standard devices like motors, solenoids, and so forth, and then how those devices then get put into control systems like the robots that you can see down here. And of course, you need integrators to take those control systems and ultimately put them into the process environments. And really what we're doing is we're really serving the customer. It's all about the consumer at the end of the day. So what we're doing is really taking anything from that sort of chip set all the way through to the consumer, and we're providing customer demand. Now, as we move across each of these ecosystems, essentially, we've got to understand that each of those ecosystems have got their own challenges. So when we're transferring information from embedded systems to standard devices, there's a whole different conversation to when we're transferring information from standard devices into control systems and so forth. And I think this is a challenge, is that what your group essentially are looking to do is how do you get that feedback back towards product design? And that's really where I see that there's this huge chasm of a lack of knowledge between those sectors. So everybody understands their own little sector, but how do you get the sort of feedback that you're looking for to develop these new systems? So, when we talk about these systems, obviously we've got some of these systems down here. We got, sensors that we just take for granted. We don't need to know how these things work. We simply need to know how they function and what extra ability they give us. So when we think about vision systems, yeah, you just pick up an Omron sensor and you just use it. So we don't need to worry about whether it's got all of these great capabilities. One of the things that we're doing here, though, is to look at some of these things like preventative maintenance. You've heard some of these things, monitoring temperatures, vibrations, and so on. And what we've done is we've developed our own product, industryweb.com, and obviously you're more than welcome to look at that and contact us afterwards. And of course, it's a box, it's an embedded system, but it's actually connecting control systems to IT systems to web systems. What you saw earlier was really some of that information just being presented on a website. And that's what we're doing through our factory system. But we're doing more than that. We're looking at these vision systems. We're looking at preventative maintenance. And what you can do now is with the types of technology that we've got, with the virtual headsets and so on, is you can literally point and click and get information at your fingertip, because all that information is already in your control system. It's all about accessing it instead of having to go up to the robot and press a couple of buttons on the controller and work it out. That information can be presented. And then we sort of take it further. So this is the sort of work that we're doing with the FactLog project. And we're now starting to look at cognitive behaviors, because you can digitize everything, but at the end of the day, you need the system to understand what it's trying to do. And this is the sort of work that we're really getting heavily involved with. And I'll be really interested to see some of the results of FactLog. And of course, again, if you want more information, contact me afterwards. But the real sort of area is this AI landscape. And again, it's how do we bring this machine learning, these natural processes, vision and so on, into the sort of systems that we're talking about. And what we're playing around with, and you'll see a demo very shortly, is we're playing with technologies like, well, obviously yellow was the start point, but we're looking at things like TensorFlow and so on. So there's an awful lot of work we're now doing on AI systems to bring them into that manufacturing area. So machine learning, vision, speech, all the things that you'd expect. So machine learning, I mean, I don't need to preach, you guys, you already know. It is all about quicker, faster, better. So, we're going from these big clumsy systems, through to these neural network sticks. And what we're looking for is just simply things to be giving you information much, much quicker. So instead of standing there for hours trying to teach these algorithms, those things are good. So it's all about improving machine operating performance. It's all about improving the user interface. That's really where we're measuring a lot of this sort of information from. And of course, the sort of systems that we're using is that you're now having that knowledge, that information, that power locally. So there's no data links to external servers. You don't need them. You should be able to have enough computational power locally. It's more secure because you're not opening up your systems to the web. And of course, we're looking for more response. It doesn't mean that we don't connect to the cloud, but a lot of the manufacturing systems are all really local based. So we're bringing this intelligence from the embedded systems all the way through to the typical activities. So speech recognition, which has been around for years, but finally we're sort of starting to really pull everything together. So instead of having disparate systems, you're now starting to get the one system in itself. And so really in summary, and that's why I've really sort of blasted through this as fast as I can, because as I said, the slides are available afterwards. What we're looking for is functionality requirements. And of course, they're going to explode with a new implementation of AI and new technologies through digitization, driving these embedded technologies to provide AI process technologies within control systems. So we're talking about code injections. This is something that a lot of the vendors are now really offering. So whether you go for Bosch or whether you go for ABB or Siemens or whatever, you can now start to inject your own code within their control systems. So you're no longer locked with the vendors. And of course, cyber physical systems for connected and collective intelligence. This is what SME Cluster effectively is all about, is pulling these things together. What we need to do is understand that it's the individual that needs to get the benefit. And if the individual gets the benefit, then it's easy to push that into business rather than the other way around. So that was my sort of quick and dirty presentation. What I'm going to do is just sort of stop sharing the screen. I'm going to give you a very quick view. So hopefully I've caught up a lot. So if I sort of, am I back on video? Hopefully. Yep, Nigel, you can see me.
Yes.
So what we're going to have is just Toby. So of course, topic of the day is COVID. So one of the things that we're using AI systems for is mask detection. So we're working with a company through one of our projects where you can actually detect the right type of mask. So it's not just about using a mask. And Toby, if you want to sort of just give us a quick sort of demonstration of what we're looking at. What we're going to try to do is actually develop a system so that people can, in controlled environments, and obviously you probably can't see it from the distance. You can see Toby is sort of showing a mask on screen. As he removes the mask, you can see that there's no mask. There's nothing too clever about that. The clever bit eventually, Toby, if you can just sort of show us the other mask that we're looking to simulate. What we've got to try then to do is to differentiate different types of masks, because in a paint shop, for example, you might be wearing a standard mask, but you can't turn certain systems on because danger. Yeah, so you're then having to start to overlay additional learning systems onto the whole thing. So again, if you're interested in some of the work that we're doing, we're more than happy to work and talk with everybody. And hopefully, Nigel, has that done you any favors in terms of catch-up time?
It has. Thank you very much, Jack.
Okay, no problem. Thank you very much, everybody.
And thank you. And that, in many ways, has provided a great link into our next presentation from Steve, which really does focus in on some of these vision systems that are coming in to the manufacturing environment. So, Steve, can I hand over to you?
Yes, you can. Thanks, Nigel. Can you hear me okay?
I can hear you, but can't see your screen at the moment.
We're just sharing it now. Okay?
Yep, that looks great.
All right, fantastic. Thanks very much, and great talk so far, guys and ladies. And I'm looking forward to building on that as we go into my deck. A little bit about AD-Link first, just in case you haven't heard of us. And I'll just make sure my screen flicks down. There we go. So if you go and search for us, we will come up as a hardware company. But actually, our tagline is leading edge computing. We are traditionally a hardware organization. We provide things from small modules all the way up to industrial PCs, very high powered devices, Intel and NVIDIA partners. And we are now moving much more into combining hardware and software. And that's where my role comes within the business. I look at solutions. And you can see here, so we've had some recognition as well as being leading in this space, which is fantastic. To keep us back on track, you just heard a lot of the partners talk about, the presenters talk about the reasons for edge computing. I don't need to go over it. I completely agree with what's being talked about in terms of the reason we need to sense, process, and act at the edge. What I want to talk a little bit about is machine vision. I think that's quite an interesting topic. We've got some use cases that I'll run through in a second. And as you heard earlier, the real task, first of all, is to build your model. You need to gather the images, mark the objects, train and test them. And as before, cloud is a really good place to do that as a platform. But obviously, we're talking about edge computing, and we want to be able to use images and sense, process, and act. And that's the aim behind edge computing, is to create some value from that data that you've collected and trained to do that. And I've seen some fantastic solutions now where you can do the training at the edge using medium to high powered devices. In terms of use cases, I want to talk about this use case in particular. We've got asked to get involved with Smart Pallet. It's about palletization. And in this use case, we're actually trying to increase employee productivity and accuracy of packing, but also reduce theft. And I'm going to show you actually some video which is taken from the camera that's looking down onto the actual pallet. So this is not the operator view, of course, because this is not what the operators want to see. They want to actually get a red or green light as to they've packed correctly the pallet. What we're doing here is we are obviously, we detect the pallets. You've got two alongside each other here. We detect the pallets, and then we're looking down to detect the boxes. So first of all, we need to read barcodes. Is the right box on the right pallet? It's green. If it's not, then it goes red. And you can see on here, we've also highlighted boxes which are red because there is no barcode. So we had to train a model to identify boxes. And the reason that was done is because obviously you then can't guarantee whether this pallet is correctly packed. But also there was, in some circumstances, this is a way that there was shrinkage. There was theft in the system where boxes were being turned over and taken off during the delivery chain. So it was, this is a way of making sure pallets were tracked and photographed. This use case is a smart pack, as we call it. So in this use case, this is for effectively, this is Girl Scout cookies in the US. And this is the way this works is the Girl Scout cookies get delivered into the third-party logistics. They are coming on huge pallets and they get repacked for distribution to customers. And you can see in this use case, we're looking at, this is actual production line. You can see the camera on the right-hand side of the screen at the top, that's reading the barcode off the box. It's sending that data back to the, ERP system, working out what should be in the box, and then looking down at the box, another camera, and detecting what cookie boxes are there. And on the left-hand side at the top of the screen, you can see a little light come on, green or red, which indicates whether that box is correctly packed. And this is edge computing with AI in action. The accuracy of this was that traditionally 75 to 80% accuracy on packing, which caused a lot of waste in the system with rescheduling customer orders and complaints. This went up to 99% by implementation of this system on the production lines. And this company will now do all the Girl Scout cookies next year by introducing Edge AI. Okay. And we've heard a lot of the discussion before in terms of devices and cloud access and so on. And one of the things we noticed in our solutions is that certainly in manufacturing logistics, the devices aren't connected to the cloud. They are typically aggregated through a gateway for the security reasons, but also because they don't need to be. We're going to do the processing at the edge. And when that data needs to go to the cloud, you can trigger that through a single device. And that's actually because, you know, IT and OT are owned by different people in organizations. And the IT team, very conscious about security. And so they basically partition the networks. So that's how we see typical deployments on sites where you have to split off. So expecting cloud connectivity for all edge devices in industry is unrealistic. The way that this works is, so you can see also here, we move the data around, and that's one of the key things we do at AD-Link on our devices and other devices, is we move the data around between different types of assets so we can connect different types of things. And I'll explain why we do that in this way. But if we think about everything we put on a device as an app, a container, then it gives that device its purpose. And then it's about where we move the data to create the actual systems that we deploy. I wanted to spend a little bit of time covering the key characteristics of data sharing systems. We've heard a lot so far in the discussions about models and training. We've heard a lot about the hardware and choices of processors. And one of the questions that was raised, quite interesting, was about how do we communicate between devices to make these systems work. One of the key things that we found is when you deploy systems into customers, is that they need the ability to evolve the system. So our data river, which we call it, which is our data bus, is built with the concept of using data centric. So it's not about the topology of your system. It's not about the connections. It's about data. So think of that a bit like newspapers. The newspaper sellers, they print the newspaper, but they don't care. They don't know who buys it, and the buyers don't care where it was printed. And it's the same concept with us when we build systems. Is you've got producers of data and consumers of data, and they can be deployed on different pieces of hardware to build a system in the most effective way. And that allows you to upgrade your systems without impacting existing systems. Also key to this type of system when you deploy is the quality of service and latency, as we heard in the discussion before, in the videos before. We needed to flash that light quick enough so that actually it made the action worthwhile. The person packing the pallet, it needs to flash before they turn around. Otherwise, it slows the whole process down. So speed is really important, and latency within that network. But also, what happens if that network gets busy? So you need to be able to describe your data in terms of what is its priority. Does it need to be reliable and always delivered, or is it just best effort and delivered if you can, but otherwise I'll take the next piece of data? And also, what's the fault tolerance? These are business critical systems. You don't want to lose your whole system because maybe part of it fails. Maybe you can continue to operate. And so these come up in discussions when we are rolling out. To be honest, my background for the last 20 years has been in military and aerospace systems, building data movement. And the military sorted this out 20 years ago. A battleship, for instance, is a great use case for an edge AI system. And they use this technology to do that. That's what we use in our data bus. And they realized that because things like, which we see in POCs all the time, MQTT, it doesn't scale sometimes to those bigger systems. You need to add more functionality into your applications to deal with some of these prioritization reliability issues when you want to scale out to larger systems. Also, customers don't want to be locked in. So they want to be able to have access to that data from the platform, whether that's the inference results or the raw data, to be able to then build on other systems. That's important for them for a cost structure. And we all know about security built in from the start is also something that needs to be done. But it's locked down in industry. They look at all the attack surfaces, and it's a key one there in crossing the divides. I wanted to look in vision in particular. So as well as being able to distribute lots of different functions across devices, there's a few key things here, and that's been highlighted, I think, before as well. When we build systems, the way we do it in AD-Link is we've got a generics video pipeline, shall we say, our vision pipeline, and connecting to manufacturing equipment as well to take actions. What we do is we're aware that the model builders, they have their own technology they want to integrate. They might want to build it for Intel. They might want to build it for NVIDIA. They might want to build their own particular inference engine. And we allow that to be plugged into our pipeline fairly straightforward. And we also take care of the distribution of the models to all the inference engines at the edge. If you've got one aggregated gateway, you want to pass the model down to that and have it share it to all the different inference streams that are running when you do an upgrade. The people who build the data science models typically don't care about integration and don't really have that skill set. They want to build the model, they want the training data. That's really what they're interested in. So we support that as well to allow you to plug and play. Different hardware choice to match your environments, so that's NVIDIA, Intel, is also possible to match the runtime engines. But also the key thing about video is it's large. In some of the circumstances, you need really accurate video frames. This can be large data, and putting them onto the network can be really painful. So the ability to choose what to put there when you're training you obviously want to put it all in there to capture it. But once it's in inference mode, the only things you want to put on there maybe the failing frame rates, frame detection where it's not a high enough percentage so that you can retrain. But otherwise, process as quickly as fast as possible on the device, and then transform it into other types of video streams if you want to view it. So that's one thing to take into account, is when you're doing that, where is your camera and vision device and how powerful is it? Other things to consider when you're doing rollouts of systems is that you have a number of people who are providing the solution parts. It's not all particularly one company. We integrate different parts of software as well. Our hardware, other hardware as well. EDLink doesn't have it all, so we need to work with our partners' hardware sometimes too. You have an AI scientist who, as I say, builds the data model. You have system integrators who go and install and customize the solutions for the particular circumstances. And you have typically a managed service provider, which will look after these devices. These are new devices being put in the field, and they need to be looked after. And you may find that your customer has all of these roles within them. They will build it and they will deploy it, and they've got model builders, or you may find they have none, in which case you need to work with your ecosystem to do that, which is what we also do with EDLink. What I would say is on the successful installation on the customer side, please be aware you will need to involve HR, and there will be changes to standard operating procedures. So please bear that in mind if you're going to go from a proof of concept to a production rollout, because people are really important in that journey. And also interesting things about different business models. So we've seen when we work with system integrators, traditionally in the past, some of them may have delivered a project and then that was their work done. With AI, they get the ability to go back and now touch up models if they have the AI model building skill. So it also applies to managed service providers. They maybe bring in some AI skills and able to do that too. So new business streams for these organizations. And customers, because of the nature of AI and being able to offer new solutions, one of the ones we did with the packing, for instance, was with a meat producer in the US, and they wanted to offer the flexibility to pack multi-product pallets to deliver to customers, rather than just one part of a certain type of meat, which was what was happening in the industry. So they now were able to provide a more flexible business model to capture a different part of the market. And customers that we work with, they want to learn about this, what we do and build in solutions. They want to have confidence. And sometimes they will take that, one of the solutions that we build with them, and they will take it to other people in their federation and create a new little business stream for them with rolling out and providing the role of a system integrator in some circumstances. And the other way that we help these system integrators and solution builders is if they are using our products, then we can help them take it to market, because EDLink does not have all the solutions or all the variations, and we can help market that back through our channel worldwide. So the way we do that is if we deploy containers, if you build a container which fits in our ecosystem, it can be sold back through. Just finally, we to make this easy and try and help people on their journey with vision, because there's a lot of parts to put together when you're building a solution. At EDLink, we built Visi AI. It's a small Intel dev kit with the Intel VPU on board, because you do need the AI accelerator to make real use here. It also comes with the software stack. So you can go from receiving the device, plugging a webcam to it, and you can be doing inference with some prepackaged models, standard ones from Intel, to texting when you see people in literally 5 minutes. And the idea there is to get you used to the concept, to use it in demos. And when you're ready for production, you can step up to other devices in the EDLink catalog that give you the higher processing power and industrial kind of casing to allow you to deploy online. We've got a community, go-to50.ai, that is specifically aimed at helping to educate as well, so that people can go there and learn. As I say, there's different actors involved, system integrators, AI modelers, and there is certainly lots of skills to be learned in putting solutions together. And I think that is me, Nigel. Does that help out as well too?
Yep, thank you very much. That's great. So what I'd ask is all the presenters, if they could turn their cameras back on. We've got about 10 minutes before we're normally due to finish at 12. We may go over slightly. And I'm going to select some of the questions from the Q&A window and pose it. Of course, we are short of time, but it's been a fantastic set of presentations. I'm not going to apologize for the length of the presentations. I picked 4 questions. If you could do shortish responses. But I think the first one I wanted to pick on was from Louis about security. And his question was, which is intrinsically safer, the AI in the cloud or AI at the edge? And also broaden that to other specific things in terms of on-chip security devices that are beginning to make it more secure at the edge. Mark, do you want to start us off on AI cloud, AI edge, more secure?
I would say that if AI at the edge was isolated, if it wasn't connected to the cloud, then it would be AI at the edge. You know, there are fewer attack surfaces, but the reality is, I think most models will be connected as well. So I don't think there's a single answer to that. So I think as long as something's got a connection, then there is a vector of attack there. If you're storing your data on the cloud, I think that's opens up obviously much more access. So there's that suggests that the cloud is worse. So I think generally, if I was to be pushed to an answer, I'd say AI at the edge is more secure, but it's a little bit more nuanced than that.
Adrian, you covered quite a bit of moving AI from the cloud to the edge. Do you want to comment? And you're on mute at the moment.
Yeah,
so.
sorry. Yeah, I think that is a natural way that we are going to move more of the AI processes to the edge. But still, there is as I said in my presentation, there is a quite big research actions to be done on data privacy and how to guarantee that the sensitive data is not that does not leave the device. I think that there is still a lot of research action to be done.
And Nicholas, have you got any thoughts?
Yeah, I think it is going to become a really pressing question, especially now with the new cybersecurity standard coming out of the IEC, the 62443. So it's going to be a question much more asked. Generally, I would say whatever you keep local is sort of harder to steal in big numbers. So of course, there are still concerns. So even if I don't send up the, let's say, smart speaker, even if I don't send up the voice, I still send up some sort of signal. So it's not enough to do security at the edge device, but you have to think it all the way through. But generally speaking, yeah, keeping stuff on the edge simplifies some things, but it's not a cookie cutter thing.
Steve, from your viewpoint, working with customers, how much do they worry about security of these systems?
That's a really interesting one, Nigel, because what we find is in POCs, not really. They're after proof of value. So they want to know, can they get it to work? When you then move to the rollout, it is about security. So in that case, they will really care about how does that get done. They have their own standards on site. And typically, as we see, most of these systems in industry, in terms of where we've been working with warehouse and logistics, their IT teams will, ask you to install extra software on the devices to be able to monitor, or to, VPN to clouds if that's the way they're going to introduce their security. And we haven't had any questions about actual device identity in terms of, when it's shipped from factory, has anybody spoofed the device on its way to the end customer, because we're doing the installs on site, and the builds. So that kind of solves that challenge, which comes up when you're doing more of the in the field ship from supplier.
Okay, thanks very much. The next question, we will make all the questions available to all the speakers and provide answers. So any I can't cover now, we'll try and get close to the event. A question from Noel about smart cities, which was really about, are we seeing new technologies that are particularly applicable to that domain? But I'd like to broaden it slightly. Is it easier with some of these situations to put in AI systems in a brand new greenfield site where there's nothing there? or are people having to work harder and harder at adding AI to existing systems? Elizabeth, you expressed an interest in tackling some of the responses to this. And you are on.
No, as the focus of this session was more on the industry side. I think it would really be worth having an own webinar with regard to smart cities and smart communities, and that would be my feedback. I think we should really, and to answer your question, I think it, from my point of view, it is easier, of course, on the green field, and it will all be about establishing the right connectivity there, and implementing it in existing cities is, from my point of view, much more difficult. But I'm not an expert on that, so I would suggest we would run another webinar maybe early next year and try to really cover a bit more these applications in that webinar.
Thank you very much. And I think I was having a talk to Siemens this morning about why AI at the edge seems to be slightly slower in takeoff in the manufacturing sector compared to some of the other sectors. And one of the points they were making was that there is equipment currently installed in factories which has got quite a long lifetime, and people are not going to just replace equipment to buy the latest one with a bit of AI in there. And that there is a real challenge of how do you add AI into an existing factory environment? Gash, you got any thoughts on that?
Yeah, certainly. I knew the question was coming my way anyway, but it's absolutely about legacy systems, and I think this has been one of the biggest challenges from a manufacturing point of view. Is that, you know, the common sort of perception is that if things are working, leave them alone. You know, don't fix something that's not broken. But added to which this sort of rate of change has come. It's been almost like a separation between the shop floor systems, the office systems, the customers, and so on. But with the advent of Industry 4, with the advent of, you know, all the sort of smart technologies, you know, we've got to get connected. And this has been the challenge, because again, a lot of people are always talking about, well, why do you need to send data to the cloud? It's really analytics you want in the cloud. When you're talking about manufacturing, you simply are working within the constraints and confines of your process. So you really need fast information at that process. So I think that the challenge really is, you know, we've been trying to push cloud computing into manufacturing, but really you need to consider what are the real applications of it. And I think that's part of the, you know, the education, because all of a sudden, and, you know, and I teach people, you know, electricians who, you know, initially we're just pressing, you know, a couple of buttons and you're teaching people a bit of relay logic. All of a sudden now you're teaching them control systems. They've got to be experts in IT. They've got to be able to upload, download files. They've got to be able to connect, you know, to all sorts of systems. So the onslaught of knowledge, certainly to the manufacturing field, is too fast. And of course, you know, that's why we're talking about, you know, this difference between evolution and revolution. It's absolutely, you know, this revolution that's come, and it's caught an awful lot of companies out. So it's about education. It's about getting people to understand these things. It's about adoption, but a lot of the new systems will come with the new builds. So that I think is the real challenge, is bringing legacy systems. And, you know, not to plug industry where, but I'm going to, but quite often a lot of these things, it's all about overlaying systems on existing legacy systems to give you some of the capabilities. So that's sort of the way forward.
Mark, yeah, thanks. Mark, did any of this come out in the survey with the engineers about legacy systems as opposed to working on new things?
No, we didn't really touch upon that, actually. We were really talking about in a slightly more abstract form about, and I think when most people answered that survey, they were probably focused on what they were doing next, new things, as opposed to adding, you know, capabilities to legacy systems. We do get involved quite a bit though I mean, we're quite heavily involved in voice interfaces, and adding voice interfaces to legacy systems is one of the things that we focus a little bit on, because you can do it. It is possible. You can plug a directional microphone in through USB into a legacy system and voice enable it. So it's definitely something that is part of our consideration as a business, is how we can retrofit some of these capabilities to things that already exist.
I'm going to ask one final question. Sorry, to try and keep to the time. We think 2 hours is probably the right thing. I'm never sure whether we should have 2.5-hour webinars, but and it's from Peter. And really, it's an interesting question. I'm going to try and see if I can get through all of you. We talk about AI systems and we get really excited about the intelligence we're trying to build in machines, but aren't they really based on neural networks and technology that's years and years old? When are we going to get really intelligent systems that have much more ability to adapt to changes? So when's superintelligence going to come and hit the market? Mark.
Thanks. Crikey! I mean, what is super intelligence? I mean, I think I think we're probably on a path of evolution so far as performance and memory density is concerned, which will ultimately constrain how complex the models are that we can house in economical platforms. So I think I noticed there was a question about quantum computing, which I was hoping you weren't going to ask. But you know, I think that those sorts of things offer the opportunity to do a step change. But for now, at least, I think we're on an incremental change based on density of compute and memory.
Nicholas, are you seeing people getting more intelligent systems than the ones we're currently developing?
That broke up on transmission. People putting more?
Do you think, does the market recognize that the technologies for AI is quite old? What we're doing is processing traditional technology faster and better at the moment with increase in performance in chips. What are the breakthroughs? Can you see a breakthrough coming where it would really change the way things were doing?
I'd say one of the breakthroughs which is still sort of echoing is this democratization of tools. I mean, a lot of these ideas are pretty old. I remember a colleague back at the Institute going like, well, we call this deep learning now. I used to call that multi-layer perceptron. And I think this sort of, that we have the tools which are available to research labs easily, that you don't need to book time on a mainframe anymore. That's a big change. And I'd say what's now sort of making the big change is that these tools are being translated to embedded systems, so that we're going away from the data center, that we find ways to reduce these complex models into something which is easily executed on simple systems. Of course, we have this ongoing set of discussions about new architectures and spiking networks, neuromorphic accelerators. So there are some very exciting ideas out there. But even today, we already see that people can just sort of pick up a hobbyist board and watch a couple of YouTube videos. And even if it's not mathematically groundbreaking, they sort of get their ideas out of their head into reality. And there's a sort of very rapid iteration happening right now. And it's interesting to watch what people come up with. And sometimes that's not what academia or what product marketing expects at all, but it's going to be something which changes things. And I think this is an exciting process to be in right now.
Gash, are you seeing excitement within manufacturing for AI?
Yeah, no, I mean, and absolutely. And I think it's not a case that there's been a delay. The requirement has always been there. But I think it's how you translate this sort of almost, you know, clunky research, and I call it clunky research, into something that's going to be quite a solid, repeatable system. You know, manufacturers, they can't afford for things just to break down. It's got to be slick. It's got to have a proven record. So, you know, you're always going to find manufacturers almost behind, you know, quite drastically the development curve, purely because they need reliability, they need repeatability. But when you start to talk about some of these, you know, vision systems and the stuff that we're doing now with this intelligent AI, you want to see robots that can see production, not vision systems, but they actually know what to do when things go wrong. So yes, we talk about cobots. Yes, we talk about, you know, humans and automation and systems working together. But ultimately, me as a businessman, I want to press a button. I want things coming out. I want lots of money. And I don't really want any humans involved. That's not the right answer, but that's really the ultimate aim. So how do we still keep humans in the loop? How do we add value to people? And that's really, again, when we sort of start to look at the next revolution, it's the fight back of humans. It's like, well, we've given everything over to the machines, they do it, but we need to think about the purposes and how we can bring almost like the human elements back into manufacturing.
Steve or Nilam, have you got any final comments?
Yeah, if you don't mind. So I think on one thing, it's about data. It's about the actual the amount of training data that's available. So to make things smarter and to be able to predict better, it's all about acquiring data. It's interesting working with simulation data. So can you simulate data to create those data sets to allow us to get smarter and see end results? So I think that's it. That's a way that's a thing that needs to happen first before we will have super smart. And also acceptance of whatever that super smart is it right? So you need to be able to validate and say why that decision is right. So proving the model is making the right decision. So knowing about how it makes those decisions is also important for, I think, super smart systems in the future to make sure we have the trust in them.
Okay, I'm afraid I am going to end it here because we are 5 minutes over the time slot, but I would like to thank all the panelists and speakers for what has been a really fascinating presentation. For the people, the delegates, if you found this useful, talk to your friends, communicate with your colleagues. We'll make the material available on the net through EPoSS and through KTN. So they'll be able to find out what happened and what they've missed, and we're sorry that some of them missed it. I'd also like to thank Natasha, Nilam and Elizabeth in particular for helping me put these together. Natasha is the person who works behind the scenes, making sure everything works and does the all the registrations, etc. But it's the backroom people that you don't normally see on a webinar that can sometimes go as the unsung heroes. So I would like to express my thanks to all those people who helped come on. So I look forward in a month's time. We'll look at mobility. Probably have a different set of presenters. If I get desperate, we may have the same presenters. It will depend. But I would like to thank everyone for joining today, and I'd now like to close. So thank you very much.
Thank you.
Thank you.
Thank you, Nigel.
Thank you.
Bye.
Bye-bye.
And